Welcome back to che531. In this video, we're going to be continuing on stiff problems. So in the last video, I talked about ODE 4.5 and 1.5s. These are MATLAB built-in functions. So in ODE 4.5, we have to introduce the function first. By function, I mean the right-hand side of the differential equation. And then we have to give the minimum and maximum points along the time axis or along the x-axis or independent variable. And then we have to give an initial or the boundary value or the initial value for the function we're trying to solve. And of course the options. So options include, maximum number of iterations, tolerance, and stuff like that. Okay, so last time we said we're going to start with ODE 4.5. If the accuracy and speed are the concern. So ODE 4.5 solves with high accuracy and high speed. If the problem has time constant, or maybe two time constants, one is much less than the other, then most likely ODE 4.5 cannot resolve it. And that problem is going to be stiff, so we're going to use ODE 1.5s. So now we're going to go over one example to see the solution from ODE 4.5 and 1.5s and basically be able to compare in what circumstance we have to use ODE 4.5 and in what circumstance we have to use ODE 1.5s. Okay, so the problem we're going to look at, and by the way, one more thing, so in these functions we can also give the time span. So the two options to provide the independent variable, one is the minimum maximum right here. Another way of looking at it is, let's say we want to solve at specific time points, then what we do is instead of giving the minimum maximum of the time value or x value, we want to give the discrete time points, like as I have here. You can have a vector t-span, and t-span is actually a vector starting from x0, ending at x final with increment of dx. So that actually creates an equally spaced x vector, and then this x vector or t-span will be used in the second argument of these functions. Okay, so let's look at one example. This is very similar to the robber problem. I have three y values, y1, y2, y3, corresponding to the concentration of species, ABC, and the rate constants for the three reactions are, something like 10 to the minus 2, 10 to the plus 7, and 10 to the plus 4. So you see that the range of rate constants are varying, something around 9 orders of magnitude. So the difference between this and that is about 9 orders of magnitude. And that means the problem has a time constant that is much less than at least 2 time constants. Okay, the time constant for this reaction is much, much less than the time constant for this reaction. Okay, and this should basically ring the bell that most likely ODE 1.5s is the way to do it, not 4.5, but we're going to try both of them. Okay, so before getting to the solution, let's remind ourselves one more time that we're going to be using most likely 3 ODE solvers from MATLAB toolbox. The very first one maybe is ODE 2.3, and this is when the accuracy is less important than the speed. So if the speed is really important and you don't know what the function is going to be whether that has 2 time constants or not. And then OD 223S maybe is the first option. If accuracy and speed both are concerned and we want to have both of them high, then we use OD15. And if the differential equation has time constants, 2 time constants at least, then one with one much smaller than the other, which actually brings the problem to the realm of stiff problems, then we're going to use OD15S. Okay. So now all we do is we have to write the right side of, we have to script the right side of the functions in ODE solver and basically solve it in MATLAB. So I'm going to switch to MATLAB script. Okay, so this is the same problems, the same 3 equations I showed before in the note. Let's say I have 3 constants A, B, C. Well, these, you can think of these as pretty much like the rate constants. So one is in the order of 10 to the plus 2, the other one is in the order of 10 to the minus 6. And you see that the difference is about 8 orders of magnitude. Okay. So we write the f as a function of x and y, and we know that while y has 3 elements, y1, y2, y3. Okay. So this is the first equation, this is the second equation, this is the third equation. I lump everything into this y, into this f vector, which is a function of x and y. And for now, let's set the limit to, let's say 1 minute. So this L means the total length, which means the difference between minimum and maximum x is about 1. Okay. So I'm going to comment this out. And uncomment the line above. Oops. Right. Now I have 10 to the 6 discrete points along the x-axis. And I initialize my y vector to be all 0. And then the initial value would be, which would be 1, 4, 1.1, and 4 for y1, y2, and y3. Okay, so I set the initial value to y0. So y0 will be now assigned to the first column of y vector. My y vector actually has 3 rows and 10 to the 6 columns. Each column corresponds to each x that I'm going to generate. Okay, so here's the x span. So from 0 to 1 with 10 to the 6 elements, or 10 to the 6 discrete points. Dx is the difference between the 2 x values. You calculate k1, k2, k3, k4. This is rk4. And I average over the k's. So this is how I calculate using rk4. For comparison, I also calculate the solution using OD45 solver. So I feed in the f function, the limits 0 and L, and then the initial value for y, which is 1.0 I calculated above. And then the output goes into x and w. So this w is actually the solution for y1, y2, y3. They're all lumped into one vector. And then at the end I'm going to plot w as a function of x in 3 panels, because there are 3 solutions, y1, y2, y3. Each of them will go to different subplot. Okay. So I think we're ready to go. Let's solve it. So I'm going to solve using RK4 that I wrote and compare it with OD45. So right now the domain length is 1, which is not really large. And that means the problem most likely is not stiff yet. Because by definition, if you remember, stiffness was lambda, the characteristic decay length, or decay time. Actually, inverse of it. It's going to be inverse of the decay time times the domain length. Now, domain length is small. I'm assuming that whatever lambda is, overall lambda times the domain length is going to be small because the domain length is small. So let's run this, and hopefully you will see quickly that the two solutions should match. There you go. So blue is the solution from MATLAB ODE solver. The blue is ODE45. My solution is also blue, which is not a good idea. Let's make one red. So I'm going to make my solution red, the one from RK4. So let's redo the problem. And we're going to see that they're almost on top of one another. So if I zoom in here, and further, and further, and further, do I see any red line here? Not really. So let's make sure that, oh yeah, actually, I'm sorry, this is in a different figure. This should be in figure 1. So let's redo it. Okay, so this, you see that this is really fast. Okay, now there's only one figure, and I'm guessing these solutions. Yeah, now I see they're very close. You see that the red and blue. Well, of course, the red is a bit more accurate because that's based on ODE45, which means RK4 and RK5, and RK5 is more accurate than RK4. So overall, ODE45 would be a bit more accurate than RK4 that I wrote. And you see that there's a little difference, there's a little error between them, and the error is about, you know, something around 1/10 of a unit. So anyways, this was really fast. Now let's go ahead and increase the domain length. So this makes the problem stiff. And say I increase the domain length to 1000. Now, I'm going to run this, but it's going to take forever. And even if it doesn't take forever, the solution that comes out would be really nonsense. So now what we're going to do is I'm going to use ODE45 as before and RK4 from my script. Okay, so let's run the problem. Okay, so this might take a while because the domain length is large and I'm using ODE45. So so I think it may take a long time to do this. But even if you stop the problem in the middle, so I'm going to stop it before it actually ends because I don't think it's going to end, very quickly. So I think, okay, so let's do that. I'm going to cancel this, but once I cancel it, you'll see that the solution up to now is completely incorrect. Yeah, it's completely wrong. So this is the solution up to now. And you see that actually so I'm going to stop it before actually doing ODE45. Let me just do this up to there. And this should be quick because the function that I wrote is just 10 to the 6. Yeah, this is the solution for RK4 in the script that I wrote. And you see that the values are no way near what we saw from the solution with domain length of 1. Okay, you see they're completely incorrect solutions. Even if you do with ODE45 in MATLAB, you won't get the solution right. This is 10 to the 200. This is completely incorrect. So in the next video, I'll show you when you switch back to ODE15S, we will be able to solve it. Thank you so much for watching. Stay tuned for the next part. in stiffness of ODEs.